Okay, so we're going to be looking at machine learning based calibration for a high-speed digital to analog converter, also known as a DAC. And in particular, we're going to be looking at a current steering DAC. So there's a whole bunch of different DAC architectures to choose from, but the current steering one offers the highest speed and becomes the de facto solution at gigahertz frequencies. And I put a quote there from Razavi and along with the reference, where basically the output current is a linear combination of binary weighted current sources, where the MSB carries the most weight and the LSB carries the least weight. And you may want to pass some current I out through an output impedance R, as shown in the diagram here. Now the problem with these DACs, like many other integrated circuits, is that they are nonlinear. So if you want to put out a tone at a frequency F out, you're going to get harmonics at integer multiples of F out. Now various impairments cause these harmonics, like current source imbalance, bit rise fall time mismatch, bit delay errors. Usually any type of mismatch is going to contribute to harmonic distortion. And this nonlinearity is actually composed of static and dynamic parts. So there are memory effects, very much analogous to a power amplifier. So the question is, can we use deep learning to come up with a nonlinear equalization scheme, which I abbreviate NLEQ, to obtain a spectrum like in this plot here, where there are virtually no harmonics and just maybe some thermal and quantization noise. Now in practice, there will be some harmonics, even with an NLEQ scheme, but the goal is to get them as low as possible. So this is like an ideal output spectrum from a current steering DAC based on a Simulink model. So we're going to use the Simulink model throughout this to gather data. The first thing that we can look at is analog post-correction. So if we think of the DAC, we can model it as an ideal DAC in summation with some error term, which I've denoted epsilon of t. So that's in the top right hand of this slide. And the question is, can we learn epsilon of t, or an estimate for the error? And if we do that, we can subtract it off from the DAC output and obtain another signal, y sub core of t, which is hopefully closer to ideal. So core in this case stands for correction. So we also have a correction DAC, which is assumed to be synchronized with the DAC that we're trying to calibrate. So here's an example of that same plot from before and the corresponding error term epsilon of t. So the question is, can we use an RNN to learn epsilon of t and subtract it off from the DAC output? So I just plotted the first 100 samples there. We may want to look at an RNN to do this because, as I mentioned, there are memory effects associated with this DAC. So the input layer I've chosen to be 128 by 10 since it's a 10-bit DAC. Basically, it's a sequence length. Each training example is a sequence length of 128 10-bit words. So that's why the input layer is 128 by 10. We go through 32 nodes GRU, a couple hidden layers, a linear activation to get an output scalar, which is hopefully close to that error term that we're trying to learn. So after we train this over 60 epochs with a batch size of 8, we can plot the true error versus the learned error, epsilon versus epsilon of t. So the true error is in blue and the learned error is in orange. So it looks pretty good. The first 100 samples anyway. It has a low mean squared error over 64K samples. And it turns out if we employ this scheme, we get a 14 dB improvement in spurious free dynamic range, or SFDR. And that's basically you can think about the distance on the y-axis here in dB from your fundamental signal to the next highest harmonic. In this case, the fifth harmonic is dominant, and it's about 58 dB below the fundamental. So it's pretty good improvement. Problem is, with that scheme, you need another DAC. So what I've labeled as core DAC in that previous block diagram, which isn't very area efficient and obviously consumes power. So can we do better? Well, there's something we can look at called digital pre-distortion, where basically we populate a lookup table whose entries are the inverse of the DAC transfer function. So when you cascade these two transfer functions together, you basically have an overall transfer function that's linear. When you pass x of n through a transfer function that's linear, you're not going to get any of those harmonics which corrupt the output spectrum. And this is a preferred solution since an additional DAC is not required. So how do we populate this lookup table? How do we learn the inverse of the DAC transfer function? So the first thing we can start off doing is learning a model for the DAC, or training an RNN to model the DAC. So where does the data come from? Well, normally it would come from the DAC itself, but for these slides it comes from the MATLAB or Simulink model. So we train an RNN to learn y hat of t, where y of t is the actual DAC output itself. So we want y hat to be as close to y as possible in the mean squared sense. So after we train an RNN to do that using the same architecture as before when we learned the error for the analog post-correction scheme, we get something like this. So in blue here we have the actual DAC output FFT, and in orange we have an RNN model output FFT, and the harmonic signature closely matches, meaning the harmonics are very close to each other. And what I also did is I added some white noise to the training data, and these other harmonics that are present in the orange plot that aren't in the blue, those actually went down. So virtually we can match output spectra, which is indicative of a good model. So we can model the DAC. We're confident that we have a good model. And then what can we do with it? So we can basically do something like in this diagram here, where to learn the digital pre-distortion engine, we can fix the RNN that we just learned, which models the DAC, and have an output target as y ideal. So that would be the output of an ideal DAC, and use that error to train this DPD engine. So what we're doing is we're fixing the weights that we just learned to model the DAC, and we're just learning the DPD so that the output is as close to y ideal as possible. So we're back propagating the error from the RNN DAC output, the difference between the RNN DAC output and y ideal. So that error is used to train this DPD engine. So that's the idea. So as far as the architecture, it's very similar to what I used for the analog post-correction. So you're seeing on the right here is fixed during training, and on the left is what we're learning. So the right-hand side is the DAC model, the left is the DPD engine. So what happens after we do this? Well, basically, you'll notice that the output of this DPD engine is a sigmoid function. 10 nodes, one for each bit, and sigmoid activation for each bit. But the problem with the sigmoid function is that it outputs values between 0 and 1. But for each bit, we need hard decisions. It has to be either a 0 or a 1. Right? So we can't have like any 0.5s or 0.32 or anything like that. So we're going to have to threshold to make a hard decision. And the question is, does that kind of ruin the mean squared error between y and y hat? Or y and y ideal, rather. So after rounding to obtain hard decisions, it looks like the sinusoidal shape is not preserved. So in blue here is our target, which is the ideal DAC output. And in orange is the output after using this digital pre-distortion. And you can see that the signal in orange is at least in phase with the signal in blue, which is what we're trying to learn, or which is what our target is, rather. But the sinusoidal shape is not preserved, and the harmonics are actually pretty bad in this case. So we'll have to figure out another way to get around that. But just to conclude, the goal is to come up with a deep neural network-based NLEQ scheme for a high-speed DAC. We looked at two methods. One is RNN-based analog post-correction, which seems promising since we can successfully learn the error from the training data. We get a 14 dB improvement in SFDR. However, the disadvantage rather, is that another DAC is required, which is not very area or power efficient. Right? So we looked at digital pre-distortion, which obviously requires some more investigation. Perhaps an architecture change or something may be required to get around the soft decision nature of the sigmoid function. And that concludes everything. Thank you very much for listening.